get the show on the road. We'll start with questions. I think we finished, or the problem set has been assigned and graded up through 130. Does anybody have any questions on any of that stuff up through 130 that you want to talk about before we get started with new stuff? Yeah, Victoria. 122? Sure. Yeah, so these ones get a little bit tricky here, right? And this is just like example C from the previous lecture. But the first thing that I'd want to do here is I'd want to take care of the fraction piece. So I'd multiply both sides by 2. And that'll get rid of the fraction there. You cool there? And then the next thing I'm going to do is multiply by 2 to the x to both sides. And the reason I do that is that it eliminates the negative exponent. Victoria, are you cool with what I did there? I skipped some algebra steps, so if you're not sure, we can certainly talk it through. So 2 to the x times 2 to the negative x, we add the exponents. X plus negative x is 0, and anything to the 0 is 1. Again, I'm happy to, clarify those things, but it's like, it's like, how much work do I really want to show here kind of question is always where we're at. So now I'm going to move everything onto one side. And what I have now is something that resembles a quadratic. And to really kind of hammer that home, I'm going to assign a dummy variable to 2 to the x. So it really, really looks like a quadratic now. Does that feel okay, Victoria? Okay. So to solve a quadratic, typically I would try to factor, use the quadratic formula. Here the leading coefficient is 1, so if I could factor this, it would be easy. However, if I try to think of two numbers to multiply to give me 1 and add to give me -6, not coming up with any numbers that do that off the top of my head. So I would go to the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So 6 squared is 36 minus 4 is 32. And the square, or 32, I know is 16 times 2, right? Why is that helpful to me? Right, because the square root of 32 then is the square root of 16, 4, times the square root of 2. And then we just reduce that fraction. Still doing good? All right. However, I'm not done because all I've done here is solve for y. I'm really trying to solve for x. So I'm going to go ahead and substitute back in my 2 to the x. And since this is really two equations with the plus or minus, I'm going to write them separately. So far, so good, Victoria? Okay. The last step is going to be to try to cancel out that exponent base of 2. What operation do we have that cancels out an exponent base? A log, very good. Now, which base of logarithm do I want to use to cancel exponent base of 2? I want to use log base 2. Very good. I want the bases to match.
No, if you never go back to the fine.
So now it's calculator time. So remember to, to make a log of a specific base like that, I press the math button, scroll down and choose the log base command. And then I can just type this in exactly like it looks on my sheet of paper. If I can press the buttons right. So I get 254. And then for the other one, just need to change that to a minus. And I get negative 254. It's quite a workout there. Happy with that, Victoria? Landon? 126. Okay. Just take my list here and open to that page so I don't have to try to remember that, because that's a lot of numbers to remember. All right. We got a lot of space there we've chewed up. 126. So we have 400 over 1 plus 95 e to the negative 0.6x equals 150. So far, so good? Okay. One major problem right away that I noticed when solving this. My variable is in the denominator of the fraction. First thing I would do is solve that problem. So to solve that problem, I'm just going to do the reciprocal of both sides. Cool with that, Landon? Yeah. Okay. Now we'll multiply both sides by 400 to get that out of there. Cool there. Next up, we'd want to subtract 1. I'm going to reduce that a little bit just to make it a little more convenient. So far, so good. And I'm not going to worry about reducing any of this because eventually this is all going into my calculator. So I'm just going to kind of do like minimal, just kind of write it the way I'm going to type into my calculator, not worry about a bunch of intermediate numbers that I'm going to have to round a million times and like destroy the accuracy of my answer by doing. Next thing I want to do is divide by 95. So far, so good. And then how am I going to get rid of that exponent base of e? Very good. I'm going to need log base e, which is called the natural log. Cool there. Last thing I'm going to do is just divide both sides by negative 0.6. It's going to be a little bit easier to write that if I just think about it as multiplying by a reciprocal, though. So I'm going to write it that way. Is that okay? Now it's calculator time. So I have 1 over negative 0.6 times natural log. I'm going to use the fraction command there so I don't have to muck around with a million sets of parentheses to get that to show up the way I want it to. So 45 over 15 minus 1, all over 95. And I get about 674. Bad looking 7. There we go. Does that feel okay?
So when you divided for negative 0.6, how did you get the negative?
I wrote it as a multiplying by the reciprocal instead of dividing.
Yes.
Just because, like, on your calculator, it's a little bit easier for me to kind of write it that. I think it's a little clearer what's going on rather than writing like log of x all over 6 or something. Like, it's a little less confusing. Like, is that inside the parenthesis or outside the parenthesis? So I just usually write it as a reciprocal with a multiplication so I'm not confused later on. It's like, should that be inside the log or is that outside the log? Because it makes a big difference. So that's why I decided to write it that way. Cool. Anybody else? Victoria. 118? Sure, dude. So 118, we have the natural log of x squared equals 4. First thing I would do is get rid of the natural log. What is going to cancel out a logarithm? We use an exponent base. What exponent base would I want to use to cancel the natural log? Not 10. E. I want the base of my exponent to match the base on my logarithm. So I'm going to do like exponent base e to both sides. And I try to write that exponent base like really big so you can't mistake it for multiplication. So I get x squared equals e to the 4th. We'll square root both sides. So I get plus or minus e to the 4th, which is just plus or minus e squared. But remember, there's a logarithmic equation, so I have to check. If I plug in positive e to the 4th into x, well, positive e to the 2nd squared is a positive number, so that one's fine. And if I plug in negative e to the 4th, negative e to the 2nd, negative e to the 2nd squared is also going to be positive, because when you square, the negative goes away, right? So both of these answers should be fine. So plus or minus e squared would be fine. Or if you wanted to write it as a decimal, you could type it into your calculator. The check is that you can't take the log of a negative number or 0. So I just have to make sure when I plug my answers back into the original that I'm not getting like a negative inside a log or a 0 inside a log. So that's all I'm doing when I'm checking. Does that make sense, Victoria? Okay. So, or you could have written it as like plus or minus 7.39-ish. But I'm cool with e squared. That's exact, which is righteous. But decimal's fine. No big deal. Okay. We cool? All right. Let's pick up where we left off in section 15.4. So in section 15.4, we're going to be looking at, this is continued also. So the first half of section 15.4, we talked about solving exponential and logarithmic equations. Here in the second half of section 15.4, we're going to be looking at applications, so like some real world applications of these exponential or logarithmic equations, and then kind of solving some of these real world contexts. So we're going to see like a handful of models here that can be used in real world that involve exponential or logarithmic equations. So the first one is sound intensity. So the sound intensity formula is beta equals 10 times log of I over I naught. So the beta here is just representing the number of decibels. Decibels is the unit we use to measure sound intensity with. Some of you guys that are like, may have heard of decibels before, because like, I don't know, if you go to like or if you're watching like a football game on TV and it's like a close game in the fourth quarter, sometimes they put like the sound meter up on the TV to show you how loud the stadium is, and they're measuring that in decibels. They'll be like, oh, it's as loud as a jet taking off today, you know, like, woo. Anyways. So the other inputs there, I is sound intensity, which is just the unit there is watts per meter squared. And then I naught is a constant. That's always 10 to the negative 12 watts per meter squared. So let's look at an example here. That a little bigger for us. Given that the sound intensity of a busy city traffic is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? Well, we're talking about sound. So right away, I'm going to use my sound intensity formula. Which are we solving for, beta or I in the question? What is it asking for? Since it's asking for the in decibels, we're looking for beta. Very good. So we just have to fill in one or two things. We need to fill in I, the sound intensity, which is given to us in the problem, right? What's the I? The 10 to the negative fifth. And the I naught is a constant. You may. So that'll be 10 to the negative 12. So if I go and I type this into my calculator, I get 70. And the unit for decibels, or the abbreviation for decibels, is lowercase d, because that's the abbreviation for the prefix deci. And then the bells is a capital B. But pretty easy problem, right? Nothing to it there. Just plug some stuff in, not even solving. The other way that this problem could go is we could give you the decibels and ask you to solve for the sound intensity, right? That would be the other way, the only other way we kind of rejigger this problem. The next application is the Richter scale. Does anybody know what we use the Richter scale to measure? Earthquakes, yeah. The Richter scale is another logarithmic scale, just like sound intensity was. Hi, how are you? Good. So this is the Richter scale. So R is the magnitude of the earthquake. The alpha is the amplitude. And we usually measure amplitude in micrometers. So when we talk about the amplitude, we're talking about like the vertical ground motion, like when you have an earthquake, the ground is moving up and down. So it's like a sine wave that's happening. So the amplitude is like how much displacement you had from like the normal ground level up and down, right? Everybody's kind of envision that in their heads. I know we're not exactly an earthquake country here, but I remember like 15 years ago there was like an earthquake outside Illinois, and when I was living in Southwest Michigan, I could feel a little bit of shaking. Like it felt like somebody was like jumping up and down in the house, and like the house, your house shakes a little bit if you live in an old house, anyways. Kind of felt like that. I was like, oh, that was weird. And then you realize a day later, oh, there's an earthquake yesterday morning. It's like, oh, that's what that was. Weird. T is the period of the associated wave in seconds. So again, when we talk about the period, we're talking about how long does it take for the earthquake or for the Earth to go from its normal level up, down, and then back to its normal level again, like when the Earth is bouncing up and down during an earthquake. And then B is a constant. That basically is like a correction factor. Because what do we know about the strength of an earthquake? So an earthquake happens at like a specific point, right? Do you remember what you call that point, earth science people? Epicenters, right? And then as you move away from the epicenters, the earthquake getting bigger or stronger or weaker? Weaker, right? So this beta is basically accounting for like, oh, we took our measurement, like a mile from where the epicenter actually was. So if I want to figure out how strong this earthquake was, I have to correct for that distance. So since the Richter scale is a logarithmic scale, what that means is that, like if you have an earthquake of magnitude 2 and you have an earthquake of magnitude 3, the magnitude 3 earthquake is actually 10 times as strong as the magnitude 2 earthquake. If you have a magnitude 4 and a magnitude 2, the magnitude 4 is actually 100 times as powerful. So like each time you're moving up 1 unit on the Richter scale is a factor of 10 in terms of earthquake intensity. All right. So let's look at an example now using this. We have the infamous San Francisco earthquake, has a Richter scale measurement of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So to do this, should be pretty clear, since we're talking about the Richter scale, that we're going to be using our Richter scale formula. Everybody agree with that? And we're comparing 2 separate earthquakes, right? One in Chile and one in San Francisco. So I'm going to create a system of 2 equations. But let's think here a little bit before we start writing this system out. It's asking about the severity. So when we talk about an earthquake severity, we're probably talking about like how big of a shake you're getting, right? So that was represented by the alphas. Everybody agree with that? Okay. The other thing let's think about, so we have 2 earthquakes. Let's assume for a moment that the measurements that are taken are at the same distance from the relative epicenters. In that case, the betas are basically the same value. Everybody okay with that? And we're also going to assume that the periods are negligibly different. So they're basically the same value as well. Again, that's happening the earthquakes. Yes, sir.
Well, so like these rules that you're saying right now, the things that we can infer, is that going to happen every time you compare like two things?
Yeah, these would be fair assumptions to make if you're ever comparing two earthquakes, is the things that, if you're talking about like how much more intense was one than the other, you have to make some kind of assumption here because we don't have the measurements for all of these in the question. All we're getting is the Richter scale measurement. So the alpha is really our benchmark for intensity. That's what we're going to be interested in. So we're going to have to assume that the T and the B are kind of the same. So the system I would write, well, let's actually put the number in. Everybody happy here? With the system that I wrote? Okay. So to solve this system, what I'm going to do, if I call this equation A and this equation B, so I'm going to do equation B minus equation A. Basically, the rule that I would use is whichever has the higher value of R, I would be subtracting the other one from that one because I want a positive number over on the left-hand side when I do that subtraction. And there's not a good reason why I feel like I need to have a positive value for R, but it just makes our lives a little bit simpler if we do it that way. And I don't know about you guys, my life is complicated enough. If I can simplify this by being like observant, that sounds like a pretty good deal to me. So I know I'm going to have to distribute that negative sign. And then 9.5 minus 7.5 is just 2. Okay. So what can I do on the right-hand side there? There's a super obvious thing to start with. Yeah, I have a plus B and I got a minus B. Hey, get out of there. Okay? Everybody happy with that? Now I have one log minus another log. What can I do with that? Well, I can subtract them, but not probably the way you were thinking. So remember, we have the quotient property from 15.3, so the previous section. So what it looks like to me is I see that. Yes, sir. Of course. You guys notice that? So that's what I would use here. And rather than writing this as like a fraction of a fraction, I'm going to write it with the division symbol there. Everybody's okay with that? Oh, Boise, look at this mistake I made. This is supposed to be the 2. And this one is supposed to be the 1. Oh, boy. Sorry about that. All right, how do I divide 2 fractions? This is a middle school question or late elementary school question. You multiply by the reciprocal. What I remember is that multiplying fractions is easy as pie. Flip the right and multiply. I still remember that back from elementary school or whenever I learned that. And that's nice because what do you see that can happen? Cancel the t's. See ya, t's. All right. Getting somewhere now. What do we have to do next? Got to get that log out of there. Get out of there, log. What do I use to get rid of that log? What's the base on this logarithm? 10. So which exponent base should I use? 10. Yeah. Everybody's cool with that? This is our answer. What is this telling me? Which one was? Yeah, the Chilean. Ugh, pen. Come on. Do that. Maybe that'll help. Everybody cool there? Yeah? Okay. Next model that we'll look at is acidity. How do we measure the acidity of a compound or a liquid? Chemistry students, what's it called? The pH. Yeah, oh that. So the pH is another logarithmic scale. So the pH is your relative acidity. Do you remember what numbers are acidic versus basic? Low numbers are acidic. High numbers are basic. The scale runs from 0 to 14. Where 7 is neutral, that's water. And then H plus in brackets, that means the concentration in chemistry when you put brackets around something like that, it means concentration. What do we usually measure concentration of liquids in chemistry? We usually use molarity, which is moles per liter. So that's the concentration of hydronium ions. That's the fancy name for the H+. Do you remember doing this kind of thing in chemistry class? Did you do, like, calculate pHs? You don't think so? But you also just don't remember much? Okay. This would have been a second semester topic anyway, so if you caught that at the wrong time of the pandemic, maybe that wasn't, you know, didn't get that far, or you didn't remember it because you stopped paying attention. You know, it happens. All right. A really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items? Well, 2.2 is equal to negative log of H plus. So what am I going to have to do to solve for the concentration of H plus? First thing I got to do is not yet. There's something I have to do before that. What's in front of the log? A negative sign. Got to get that out of the way first. Then I'll get to the log. So multiply both sides by a negative or divide by a negative, whatever your fancy is. They're doing the same thing. Okay. Now how do I cancel that log out of there? Which means exponent base 10. Yeah. So if I go to my calculator, bless you, you're welcome. 10 to the negative 2.2 is about 0.0063. Oops. So if I do bleach, we basically do the exact same thing, right? I'm going to cheat the work. Everybody's okay with that? It's the exact same steps. So I get 6.31 times 10 to the negative 11th. What does that mean? Means 10 zeros and then that 631. Ew, wow. So last one says, how many times greater is the concentration of bleach than lemon? I think it probably should have meant lemon than bleach, right? The lemon has a lot more than the bleach does. So when it asks for times more, what I'm really just going to do is that lemon concentration divided by the bleach concentration. since I have those numbers on my calculator, I'm just going to use this one divided by this one, and I get that to be about, we got there, how many, so 1 with how many zeros there? I can't count, it's so hard. 1, 2, 3, 4, 5, 6, 7, 8. So we'd have a 1 with 8 zeros at the end. So 100 million times. Woo! That's 1 sour lemon. We okay with that? All right. One more model, one more example, and then we're outie 3,000 for the day. All right, our last model is Newton's law of cooling. So, you ever warm like 2 different things up in the microwave? Notice that they cool down at different rates? Right after 10 minutes, your pizza roll is still scorching hot, but your bowl of soup is cold or something? Newton's law of cooling is what's going on here. Let's write out what this model is. But it's basically describing the rates at which different things cool. Oops. So T of T is the temperature, T minutes after the heat is removed. So after the, like, you take your pot off the stove, or you take after your microwave goes off, after you pull your sword out of the furnace, if you're an medieval blacksmith or something. Everybody's cool? Tm is the temperature of the surroundings. Oops. So most likely that's the air in the room. Or if you're like a medieval blacksmith, maybe you pull the sword out of the furnace and you stick it in some cold water to, like, I forget what, anneal. I think that's annealing is what that part of that process is, where you're trying to make the sword really thin and hard and sharp. T naught is the temperature of the substance after you remove it from the heat. And maybe we'll say when. K is a constant, and that constant is specific to the substance. So that constant is different for, a pizza roll than it would be for an iron sword. Or a bronze sword if you're really going back in time. If you're an Egyptian warrior or something, pre-Iron Age. And then T is just your time in minutes. let's do our final example problem here today. Yay! Oops, that's not what I want. All right. A hard-boiled egg is heated to 96 degrees Celsius and then placed in a pot of 16 degrees Celsius water to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. Find how long it will take in total to cool the egg to 20 degrees Celsius. That's about room temperature. All right. So when I read this, I read two separate questions here. So the first sentence is going to be figuring out the model. That's the information I'm going to use to figure out all the values in my model. And then the second sentence is going to be take the model that I constructed in the yellow sentence and use it to solve that particular instance. Everybody okay with like the two parts there? You'll see as we go, if you're not. So hopefully nobody's confused that we should be using Newton's law of cooling here, since we're talking about, hard boiling an egg and then cooling it down. If anybody's ever cooked hard-boiled eggs, this is the pretty standard method you use to cook a hard-boiled egg, is you boil it in water, let it sit for so long, and then you toss it in a pot of cold water to keep it from cooking. So you get like your nice, end up with like a green yolk or whatever because you've overcooked it a little bit. Oops, that's a minus sign there. Okay. So let's start filling in values. The 96 degrees, where does that go? That's the T naught, right? That's the temperature of the egg when you remove it from the heat source. Where does the 16 go? Tm, that's the temperature of the medium, right? That's the cold water that we're dumping our egg in. Yoo-hoo. Okay. And we have 4 minutes. What's that going to be? The little t. And what's the 45 degrees? That's the T of T, right? That's the temperature it is after those 4 minutes. So what am I going to be looking for then in this first piece? Have to figure out the constant of cooling for an egg. Everybody cool with that? All right, let's get to it then. First step I'd want to do is subtract the 16. Very good. When I do that, I get 29. 96 minus 16 is 80. I'm going to just do that. And 4 times k is 4k. Next up, what should I do? Not yet. I got to do something before I can bust out that natural log. What do I have to get rid of before I do that? The 80. Yeah. How am I going to get rid of the 80? Divide it. Yeah, divide both sides by 80. Then, as Landon suggested, we can bust out that natural log to get rid of the exponent base e. And the last step would be divide by -4. I'm going to write it as a reciprocal, or multiplying by the reciprocal, because it's a little bit clearer when I go to look what I'm going to do, rather than writing it as dividing, because I still wonder, is that division supposed to be happening inside my log or outside my log? And it definitely matters. So I just don't want to confuse myself. So that's my K, about 2553. So my model then everybody's okay with that? So this is like my yellow piece. Okay. All right. It then says find how long. So we're solving for what here? T it will take to cool, or in total, to cool the egg to 20 degrees Celsius. Okay? So I need, what's this 20 degrees then going to be? T of T. Very good. So we're going to solve, oops, that's a T there. That's a T. All right. So solving for T, first thing I should do is minus the 16. Next thing I should do is divide by the 80. Next thing, natural log. Is this looking familiar, guys? Okay, and the last thing would be to divide by the negative 0.253. Again, I'm going to write that as multiplying by the reciprocal. And I'm going to use the ANS command here so I get a super accurate answer. Right, I'm going to use the entire decimal for my previous answer. And I get about 11.81 minutes. What's 0.8 of a minute? Like 80% of a minute's what, like 40 something seconds? 49 seconds is what I have written down in my notes. You don't need to be that precise. 0.81 is totally cool with me. All right. That was our last example. At this point, you guys should be able to do 131 to 138. That'll go into next week's problem set. And I'm going to get out of your way and let you get cracking on whatever is the highest priority thing for your life.
That's it.